in the first example problem for the section, we have a square loop of wire that is 18 centimeters on a side. So here is my square loop, 18 centimeters on a side. And in total, there are 200 loops of wire here. So 200 loops total. And this is 18 by 18 centimeters. So 0.18 meter by 0.18 meter. Now, coming perpendicular to this loop, there is a magnetic field that begins with a strength of 0, but it is gradually ramped up until it is 1/2 Tesla. So perpendicular to this loop, there is a magnetic field. I could draw that in red. And the magnetic field here is B, goes from 0 to 0.5 Tesla in 0.8 seconds. Now, the induced voltage, or the induced EMF, the amount of voltage that we create is given by curly E is equal to negative N change in magnetic flux over change in time. The change in time in this problem is the time from the initial to the final. That's going to be the 0.8 seconds. The number of loops of wire that we have is 200 loops. This is not really one loop, but this is 200 loops on and on and on, around 200 times. And then we have a change in magnetic flux. So we will have an initial magnetic flux and a final magnetic flux. So I'm going to find both of those. So magnetic flux is given as magnetic flux is equal to BA cosine of theta. Now in this problem, the magnetic field is directed perpendicular to the loop of wire. So in this case, because the magnetic field is perpendicular to the plane, the angle between the area and the magnetic field is going to be 0. Now, you could go back, refer to the PowerPoint slides and see what I mean by how we define what is the angle. So the surface of this plane comes out, the magnetic field comes out, they're both in the same direction, so I get cosine of 0. So I could say the initial magnetic flux, I'll call that phi initial, would be the initial magnetic field, which is going to be 0 times the area, 0.18 square, times the cosine of 0, 0.18 length times width, and then this gives me, well, I'm multiplying by, because the magnetic field initially is 0 anyway, so I get phi initial is just going to be 0. The final value for the magnetic flux is going to be 1/2 Tesla times the area of the loop, which is 0.18 square, times again the cosine of 0. And when I put these numbers into a calculator, I get the final magnetic flux is going to be equal to 0.0162. And Tesla meter square is the unit, but the unit won't really be that important here. So what do I get? Well, I could go back to find the amount of induced voltage. And so the induced voltage is going to be, we have 200 loops. The change in flux is final minus initial. So delta phi will be 0.0162 minus 0. And the change in time is 0.8 seconds. Phi final minus phi initial, that's my delta phi. Change in time, 0.8 seconds. I plug this number in a calculator and I get the induced EMF is 4.05 volts. So I get this as negative 4.05 volts. Now in these problems, we don't really care about positive negative sign yet. The negative sign is just indicative of whether the current in the wire will flow clockwise or counterclockwise. And we have not yet addressed this question. So I'm going to say that the induced voltage in this problem is 4.05 volts. So the induced voltage is 4.05 volts. Now the next part of this question says, if this loop has a total resistance of 2 ohms, what is the induced current? And this part of the problem, all we say is, if we have a resistance of 2 ohms, then I just use V equals IR to find the induced voltage will imply the existence of an induced current. So the induced voltage of 4.05 volts is equal to the induced current times the resistance, and I get the induced current is going to be 2.025 amp for my induced current.